Hello everybody, this is section 6 of PLC programming from scratch, and we are about to start lobbing code. We are about to write the first parts of logic in any program. So hopefully you're up to speed on everything we've discussed up to this point. And if you are, you should have no problem keeping up and comprehending what's going on around you. If you maybe missed a little bit of one section, now is probably a great time to go back and take a refresher course. Otherwise, let's jump right in. We are looking at a new program. This is our main ladder, and we don't even have a single rung of logic in there. So I've gone ahead and configured my I/O modules. I gave us an 8 input digital module on slot 1 and an 8 digital output module on slot 2. And neither of those require any type of configuration. Once they're installed on the actual PLC and then configured right here in the configuration window, we are ready to go ahead and start programming them. So we are going to be putting the I/O logic into ladder 4, which we've designated as our I/O ladder. But first, we know that this ladder is not going to run unless we call it. So while we're in main, let's go ahead and click on New Rung, and let's put in a JSR and refer it to ladder 4. So we'll just type a 4 here, and then we'll give it a description, I/O. So now, the only rung of code that we have in our main program file is a jump to subroutine 4. And that is going to call on this ladder, which is where we're going to put our I/O logic. So, let's get started. We're going to go ahead and start putting in some digital inputs. So I'm going to create a few new rungs, and when we try to compile a program, if you have any spare rungs like this that don't have anything on them, you will get an error from verification. So we do have to use all of these rungs or clean them up when we're done. Otherwise, we get these rung has no instructions and an exclamation mark at the end, which basically means the software is yelling at us, and rightly so. Now, going back to our I/O configuration window, you remember when we installed our I/O modules that there are slots over here on the left of this window. Slot 0 is our PLC. Slot 1 is our 8-channel input module, and slot 2 is our output module. Well, we're going to start with inputs, so we're going to be looking to slot 1, channel 0 for our first digital input. So coming up to rung 0, that's the first rung in our I/O ladder, we're going to put in an examine if closed instruction, and we're going to address that as I for input, colon 1 because it's module 1, slash 0 because it's channel 0. And as soon as we hit enter, we get a pop-up looking for a description and a symbol. Now, a description is used within the program. That is something that we use when we're looking at the ladders to know what that bit is, what that address location holds or does, so that we're not just looking at alphabet soup trying to figure out what N72 is and what F838 are. So we're going to go ahead and say we have a power switch coming into input module 1 channel 0. So let's go ahead and describe this as power switch input. Now down here on symbol, this is something that we may or may not want to use. When we're setting up an HMI later on, we're going to be able to see some of these addresses within the program, and we won't be able to see the descriptions. We'll be able to see addresses, or depending on the protocol we're using, we'll be able to see symbols if there are symbols. So if this is anything we're going to be possibly referring to in an HMI later on, or looking at from a different SCADA system or something along those lines, we want to go ahead and give it a symbol. But for reasons which I'll explain later on in this lecture, we are not going to give it a symbol because we do not plan on referring to this input directly down the road. So right now we have this instruction which is looking directly at channel 0 of our input module. Imagining that we have a switch connected to that channel and it's wired correctly, when our program is running and that switch is closed or in the on position, this element of this rung is going to be evaluated as true. And when that switch is in the open or off position, this I:1/0 bit is in our data table is going to be equal to 0, which means this instruction, which is an examine if closed, is going to be evaluated as false. So what are we going to do if this input is closed, if the switch is on, and if this evaluates as true? We're going to energize 1 bit, and we're going to address that from our data table. We already have one data file by default given to us, which is full of binaries, which are bits, and that's B3. So on our output energize output instruction that we just added to rung 0, we're going to address it as B3, and by default it's offering me the first unused bit in that data file, and that is B3:0/0. Now I can use that one, or I can decide to use any other bit that I want. I could use B352 or B31011, or I could go back to my data files on the project navigation pane and I could define a completely new data file, B9, and fill it full of binary as well. But in this case, let's not make it too complicated. I'll go ahead and take the default of B300. Again, anytime we introduce a new bit or float or integer into our program, we're prompted for a description. And in this case, I'm going to describe it as power switch bit or simply power switch. Now, if you remember when we set up our examine if closed, which is reading directly from our input module and channel 0 where the power switch is connected, we opted not to enter a symbol, and I said I would explain why we don't want to refer back to that input directly. The reason is we're going to set up this bit on a one-to-one direct correlation with our input, which means anytime the power switch is closed, this bit, B300, is going to be energized. And anytime that power switch is open, or in the off position, this bit is going to be de-energized. And we're going to use this bit throughout our program, in our HMI, in a host SCADA system, anywhere else we want to know about the power switch, we are only going to look at this bit. And we're going to go ahead and call it power underscore switch because no spaces are allowed in the symbol. And now you see our description appears in yellow and our symbol appears in green. Now that symbol will be visible in other systems depending on what type of protocol they're using to communicate with this processor. But power switch description does not get loaded into a PLC, it disappears. So the only thing that anything else will be able to see is a symbol, and only if we apply one. So the million-dollar question at this point, why are we setting our input up to talk to 1 bit? Why are we using a bit instead of just looking directly at the power switch everywhere throughout our logic? And the answer to that is it's a best practice to do it this way and with very good logical cause. What happens all too often in a program's life cycle is it has to be changed, it has to be revised. And it's a favorite pastime of electrical engineers to remap I/O on a whim, or just to make it look better, or to make the wires fit better in the control panel. For whatever reason, if we need to move our power switch from channel 0 to channel 5, we want to make that change in exactly one place. What we don't want to have to do is to hunt the power switch down in 30 different locations from throughout our program and make that change in every single one of them. That 3-minute change that the electrical engineer made is going to take you an hour to straighten out in the program, and then you'll probably miss a spot or two and end up with all kinds of crazy bugs. So for that reason, we segregate our I/O. You'll see other programmers that do not segregate their I/O, and you'll see them put I:1/0 throughout their program in all different ladders. They'll tie it to alarms, and whenever they have to change something, they're the ones pulling their hair out. The wise, the smart programmer will pull all of their I/O out of the logic and set it aside somewhere in a ladder or 4 ladders dedicated to I/O. And I10 is going to appear one place and one place only within this whole program, and that is right where it is right now in ladder 4, rung 0. Anywhere else will be this B3:0/0, and it might be 100 different places. That's fine. I will never need to change this bit. If there's ever a change to the electrical diagram, or another thing that happens from time to time, the input channel on the module breaks and stops working. And for that reason, we usually design a PLC to have maybe 25% additional spare input and output channels. So we will simply move that power switch to one of our spare channels, and that's going to require a program change. If your I/O is segregated and isolated from the rest of the program, you will have to make that change in one place. It'll be a 5-second change. You won't even have to test afterwards. It'll be ready to go. If you didn't set your I/O up this way, you're going to have a busy day. Just like we set our inputs up to energize a single bit in our data table, when we put an output into our logic, we're going to write it the same way, only in reverse. We will start with an XIC, another examine if closed instruction. We will give that a binary address. This time I'm using the next available bit, B301, And let's say we're working with a light bulb, which is a famous example of mine. So I will have a bit described as light bulb, and since this will be the bit that I refer to if I want to see the state of the light bulb anywhere else in my program, and more importantly, this is the bit that I'm using to control the light bulb, I'm going to go ahead and call this light bulb with an underscore because you cannot use spaces and symbols. And I will tie that bit to my output. Now, if we remember back in our I/O configuration, we put our output module on slot 2. So just like we referred to our input, our power switch on input I:1 for slot 1 /0 for channel 0. Now we are going to address O for output :2 for slot 2 /0 for channel 0 of that module, which is currently undefined, and we're going to give that a name, light bulb output. And we won't need to give it a symbol because we are never going to look at this bit. We are never going to show this bit to another system. The only thing that bit is going to ever be concerned with is the actual output. Otherwise, if we ever want to know what the light bulb is doing, or if we want to control the light bulb, we are going to look at this bit, B3:0/1. And that, just like our power switch bit, is going to be propagated throughout the whole program, referred to on the HMI and anywhere else we need to. And if we ever need to change channel of our light bulb output, we are going to have to do it in exactly one place. This practice, which I'm repeating so redundantly, is called segregation, segregating I/O. It is a best practice, and it's one of those things that if you don't do it, you will learn the lesson the hard way and you will go back to it.